Hello everyone, welcome back. We are going to do one more modified Atwood's machine, and this one is going to involve an incline. This will be the last one we do because I can make 100 of these. But in the end, what it comes down to is whether or not you have the technique down. Once you have this technique down, you will be golden. So here is our new system. I have mass 1 on an incline. I have a string over a frictionless massless pulley, which is connected to mass 2. And there will be friction later, but first I'm going to show it to you without friction. As usual, I'm going to start with my force diagram. I will start with mass 1. I have force Earth on 1, which is M1G. I'm going to split this right now. So I split this force perpendicular and force parallel. How do we get these? If you remember, this angle will match this angle in here in my right triangle. Therefore, force perpendicular will be M1G cosine theta, and force parallel will be M1G sine theta. Now that I've broken up force Earth here, I will not be using this. I will be using its components. Matching force perpendicular will be force normal on 1, which would again be M1G cosine theta. Force normal is preventing this block from going through the ramp. I also have tension 1. It looks like it for mass 1. For mass 2, again, we will start with force Earth on mass 2, which is M2G, and upward, I have tension 1. So if I was to make an acceleration equation right now without friction, it would look like this. Acceleration, F net over mass. I will make this direction positive. So for mass 1, positive is up the ramp. For mass 2, positive is downward, which means I would have M2G minus force normal cancels out with force perpendicular here. This side of tension 1 cancels out with this side of tension 1, which means the only force left is force parallel, and that is in a negative direction as I defined it. So it would be minus M1G sine theta over mass 1 plus mass 2. If this system had no friction, this would be the acceleration equation right here. Now, there's something I want you to notice. If this system was at rest, it can move either way. It depends on which force is stronger. If M2G is stronger, force Earth on mass 2 is stronger, this whole system will move in the positive direction. If force parallel on mass 1 is stronger, M1G sine theta, then this whole system would start accelerating in the negative direction, and that is perfectly fine. Once I decide which way is positive, I need to stick with that. Now, what if I involve friction? If I involve friction, I need to figure out what direction the frictional force is going. There's no friction on mass 2 because it's not touching on the surface. So there would be friction between mass 1 and the incline. However, first I need to have an understanding of what direction mass 1 is moving in before I can put down friction. Because if mass 1 is moving down the ramp, then friction is up the ramp. If mass 1 is moving up the ramp, then friction is down the ramp. Friction will always oppose the direction of motion. Now, for this problem, I'm going to make the assumption that the system has a velocity in this direction. So the velocity is in the positive direction. Notice I'm not saying acceleration. I'm literally saying the velocity is in the positive direction. And if the velocity is in the positive direction, that would mean force friction on 1 would be in the negative direction. It'd be this way. And that would be mu M1G cosine theta, which is mu times force normal. So my assumptions right now are this. I have mass 1, mass 2, theta, and mu. Let's find the acceleration, and let's get tension 1. For the acceleration, the only thing I'm going to do is make an adjustment to this equation I have in the upper right-hand corner. It'd be M2G minus M1G sine theta, which is force parallel, minus this frictional force, because it is down the ramp. So it would be minus mu M1G cosine theta. Keep in mind, if this system was moving down the ramp, in other words, if I made velocity the other direction, the only thing I would change is this would be positive instead of negative. That would literally be the only difference. From here, now let's go after tension 1. We're going to use the same technique. First, I'll isolate mass 1. If I isolate mass 1, I get acceleration of 1 is F net over mass, which would be T1 minus M1 G sine theta minus mu M1 G cosine theta over M1. Therefore, T1 would be acceleration times mass 1 plus M1 G sine theta plus mu M1 G cosine theta. This would solve for tension 1. I could also use mass 2. In fact, that looks like it'd be a little easier. I'll do it down here. Acceleration of mass 2 would be, again, F net over mass, positive minus negative, which would be M2G minus T1 over M2. Therefore, T1 equals M2G minus M2 acceleration. These are my two tension equations. This is my acceleration equation in base terms, which means once I have acceleration, I have it for each of the individual pieces of the system. So once I get acceleration, I now have this value, and the only thing missing would be T1. So I wanted to show you this one in order to show you how an incline works with a multi-object system. But just to show you, I could have any of these situations you see on the screen right now. And I just made these up pretty quickly. You can literally make 100 different situations here, but they all use the exact same technique. Once you get the technique down, you can essentially solve any of these. So practice makes perfect. As I said before, a good practice for you would be to make up some numbers for these givens and actually solve through one. You know you're on the right track if you actually get the same tension both ways. All right. I hope this helps you out. Have a good day. This is Mr. M signing off.